In computational complexity theory, Ni is the complexity class containing decision problems which can be solved by a non-deterministic Turing machine using a logarithmic amount of memory space. Ni is a generalization of L, the class for log space problems on a deterministic Turing machine. Since any deterministic Turing machine is also a non-deterministic Turing machine, we have that L is contained in Ni. Ni can be formally defined in terms of the computational resource non-deterministic space as Ni equals NSPACE. Important results in complexity theory allow us to relate this complexity class with other classes, telling us about the relative power of the resources involved. Results in the field of algorithms, on the other hand, tell us which problems can be solved with this resource. Like much of complexity theory, many important questions about Ni are still open. Occasionally Ni is referred to as RL due to its probabilistic definition below. However, this name is more frequently used to refer to randomized logarithmic space, which is not known to equal Ni. Ni-complete problems. Several problems are known to be Ni-complete under log space reductions, including Saint connectivity and two-satisfiability. Saint connectivity asks for nodes S and T in a directed graph whether T is reachable from S. Two-satisfiability asks, given the formula of which each clause is the disjunction of two literals, if there is a variable assignment that makes the formula true. An example instance, where indicates not, might be containments. It is known that Ni is contained in P, since there is a polynomial time algorithm for two-satisfiability. But it is not known whether Ni equals P or whether L equals Ni. It is known that Ni equals co-Na, where co-Na is the class of languages whose complements are in Ni. This result was independently discovered by Neil Immermann and Robert Silipsey in 1987, who received the 1995 Gödel Prize for this work. In circuit complexity, Ni can be placed within the NC hierarchy. In Papadimitriou 1994, Theorem 16.1, we have, more precisely, Ni is contained in AC1. It is known that Ni is equal to ZPL, the class of problems solvable by randomized algorithms in logarithmic space and unbounded time, with no error. It is not, however, known or believed to be equal to RLP or ZPLP. The polynomial time restrictions of RL and ZPL, which some authors refer to as RL and ZPL, we can relate Ni to deterministic space using Savage's theorem, which tells us that in any non-deterministic algorithm can be simulated by a deterministic machine in at most quadratically more space. From Savage's theorem, we have directly that this was the strongest deterministic space inclusion known as of 1994. Update. Since larger space classes are not affected by quadratic increases, the non-deterministic and deterministic classes are known to be equal, so that for example we have PSPACE equals NPSPACE. Probabilistic definition. Suppose C is the complexity class of decision problems solvable in logarithmic space with probabilistic Turing machines that never accept incorrectly but are allowed to reject incorrectly less than 1/3 of the time. This is called one-sided error. The constant 1/3 is arbitrary. Any x with 0x less than 1/2 would suffice. It turns out that C equals Ni. Notice that C, unlike its deterministic counterpart L, is not limited to polynomial time, because although it has a polynomial number of configurations it can use randomness to escape an infinite loop. If we do limit it to polynomial time, we get the class RL, which is contained in but not known or believed to equal Ni. There is a simple algorithm which establishes that C equals Ni. Clearly C is contained in Ni, since, if the string is not in the language, both reject along all computation paths. If the string is in the language, an Ni algorithm accepts along at least one computation path. An AC algorithm accepts along at least 2/3 of its computation paths. To show that Ni is contained in C, we simply take an Ni algorithm and choose a random computation path of length n, and do this 2n times. The only problem is that we don't have room in log space for a binary counter that goes up to 2n. To get around this, we replace it with a randomized counter, which simply flips n coins and stops and rejects if they all land on heads. Since this event has probability 2n, we expect to take 2n steps on average before stopping. It only needs to keep a running total of the number of heads in a row it sees, which it can count in log space. Because of the Immermann-Silipissi-Saini theorem, according to which Ni is closed under complements, the one-sided error in these probabilistic computations can be replaced by zero-sided error. That is, these problems can be solved by probabilistic Turing machines that use logarithmic space and never make errors. The corresponding complexity class that also requires the machine to use only polynomial time is called ZPLP. Thus, when we only look at space alone, it seems that randomization and nondeterminism are equally powerful. Descriptive complexity. There is a simple logical characterization of Ni. It contains precisely those languages expressible in first-order logic with an added transitive closure operator.